it?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Hello, can you see it?
Yes, we can.
Yes,
Yes.
ma'am.
क्या हुआ लक्ष्मण, कुछ बोल नहीं रहे हो? Who all are there? Sachin Kumar Singh, Mehta Alam. Nobody is speaking, so I don't know whether you can hear me or not. Anyway, so this is, if you can see it, let me see the chat box. हेलो, हाँ,
हम आपको सुन पा रहे हैं।
और मेरा शेयर हुआ, शेयर हो गया, तो मेरे पास आवाज क्यों नहीं आ रही? ठीक है, ओके, हाँ शेयर, ओके, ओके, सो शेयर हो रहा है, ठीक है. सो दिस इज आवर लेक्चर 11 and what I wanted to know about is the exam. Is there an exam before 8th we have to conduct, right? Can't hear anybody.
Don't know, ma'am.
Huh?
I don't know the exam of this course.
Ma'am,
हाँ,
11.
you don't know. पर बताओ, कोई एग्जाम लेना है ना 8 तारीख से पहले?
Yes, ma'am. ऐसा कुछ शेड्यूल तो है.
11.
मैम 11 नवंबर.
क्या?
11th नवंबर.
11 नवंबर से पहले लेना, तो कैन यू ऑल डिसाइड अमंगस्ट योरसेल्फ कि व्हाट वुड बी द सुटेबल डेट?
मैम अकॉर्डिंग टू एग्जाम शेड्यूल जो प्लाज्मा फिजिक्स का एग्जाम है 11 नवंबर का है. 11 नवंबर
Before 10 p.m. 10 a.m. Sorry.
10 a.m.
10 a.m. the ending time.
एंडिंग टाइम, उससे पहले कभी भी ले सकते हैं, राइट?
Yes,
Like that we can take
No.
before that. It's a Wednesday 10. I think they have said that you can take any time before that.
पर मैम पहले एग्जाम है उसके.
But ma'am, we have other exams too.
हाँ,
We have other exams also, no?
सुनाई नहीं दे रहा, ठीक से बोलो.
Ma'am, we have other exams scheduled on 8th,
हाँ,
9th, 10th.
इसलिए आई एम गिविंग इट टू यू कि 11th मई को 10 बजे से पहले जो खत्म होना है, तो शैल वी पुट द डेट 11th ओनली?
Yes, ma'am.
Yes, ma'am.
Okay, so 1 hour exam. So we start at around 9 to 10.
Ma'am,
Yes,
8:30
ma'am.
would be fine because it takes time to send the sheets.
Okay, 8:30 we will start. ठीक है, fine. 11 November 8:30, fine. Okay.
Okay.
Before that, I'll try to send one assignment sheet so you get an idea. It will be simple exam. And so we were talking about, we had completed the drifts, and we were talking about the fluid description of plasma, and that is a simplified description, and it helps in predicting some of the physics phenomena, and a lot of them, in fact, all the waves properties can be described by fluid equation of motion, etc. So what we had discussed is that in the last class, that if you have for any particle in a particle picture, you have to do write the Newton's equation of motion, which is this m dv by dt, and that for a charged particle becomes equal to q, and this is E plus V cross B, which is the Lorentz force. Okay. Now, if the physical picture I had provided you last time, that how does a fluid picture differ from the particle picture? Because in a fluid picture, the observer is sitting in a lab frame. Okay, so observer is here in a lab frame, and the fluid is flowing past him. So it is not, he is not following a particular fluid element, but he's standing here. And so there are a lot of observers standing at all these occasions, and they are seeing the fluid flow past them. Whereas in the particle picture, you are on the particle, the observer is on the particle and it's moving with that. So that's the difference. And then, so here we had noticed that the velocity in the fluid frame, in the fluid description, what happens is that both x and t are independent variables, because see, equation of motion, etc., are all differential equations, right? So you have to specify your independent and dependent variables. So in the fluid description, by x I mean position and time, both are independent variables. Whereas in a particle description, you are talking about the location of the particle, which depends on times, and so the particle position is now x, and time anyway is an independent variable. So in that case, in a particle picture, only time is an independent variable. You have x as depending on time. X is the location of the particle, specific set of particles or a particle, and its velocity. Both of them are dependent variables. So to go from a particle to a fluid equation of motion, you simply have to notice that now the velocity will depend both on space. Velocity here is different compared to velocity here. And if an observer is sitting here and there is another observer who is here, then they will tell that the value of fluid velocity here, and let's say this is x1 location and this is x2 location, then he will measure here velocity at x1 for all times. And this one person here will measure velocity at the location x2 for all times. So V depends on position, and this x1, x2 entire space you have. So V depends on position and as well as time. So now this total time derivative, which appears in the Newton's law of motion, has to be written like this in the partial differentiation sense, which will be partial differentiation of velocity with respect to time, where the location is fixed at the same location, plus you will have dv, which depends on the position. Let's say if we are using Cartesian coordinate system, then this will be dv by dx, and here you will have dx by dt. Similarly, you will have dy by dt and del v by. And you will similarly have the third term in the Cartesian set, which is dz by dt and dv by dz. Why I'm writing in an expanded form? Because then you will understand the dot derivatives. Now, what are these three? This is simply x component of velocity. This is the y component of velocity. This is the z component of velocity. So you have three components of velocities, and so it is vx dv by dx, it's vy dv by dy, and vz dv by dz. So that becomes this simply becomes as dv by dt plus v dot del v. Okay, you can see now v dot del v. So it will be vx d by dx, vy d by dy, vz d by dy. So that becomes the left hand side, and then the right hand side is q by m, and there is a e plus v cross v, which is the Lorentz force. And this is the equation now you need to solve. But then we also discussed that for the fluid equation, you will have an extra term here, which is minus grad by n. How does it happen? We will see it. And then there is a continuity. So this is the momentum known as the momentum equation. Okay, and this term here is known as the convective derivative. Okay, this is known as the convective derivative. It is responsible for the convection of the fluid. Then an important thing comes of mass conservation, or a number of particle which is supposed to be conserved. And that gives rise to the continuity equation for mass or number density. So mass and or number density because the number of particles are total number of particles are fixed, they cannot change. The mass is also fixed in the system, right? So we are not here generating any mass or generating any charge particle. So for the case where, there is fixed number of charge particles, ions and electrons. So that means you are not adding here the physics of ionization or recombination, because if there is a physics of ionization or recombination, then mass or number density of charge particle will not be conserved. So if you consider that mass and or number density of charge particles are, or any kind of particle is conserved, there is no creation of it, there is no I mean, like you are not destroying it also. So then mass and number density is conserved. But even then, there will be, let's say n is the number density. So mass density or number density. N is the number density if you have. Okay. Till we have time. It's the total n which is not changing. So if you have a volume here, then, and you are looking, and your entire system is a bigger thing. Okay. So your system volume is big, and you are looking at a local small volume at some location x vector. Then the total number of particles here, the total number in the system is not changing, but the total number of particles here will change, can change, because there is constant particles may be entering here, and they can also be leaving. So that would be like addition, and there will be a lot of particles which may leave also. So if the incoming rate is higher than the outgoing rate, then this particular location, the number density will increase with time. But if the incoming rate is less than the outgoing rate, then the number density here will decrease with time. Okay, so it just means, conservation means that you have dn, the total number in the system, that is 0. dn by dt is equal to 0. But what is n? N is total number. How is related to small n, which is the number density at a particular location? This is related to it by n is space integration. So it's like a volume integration of n dq r. Okay, so total number would be when you have these n's defined at number density defined at each location, and then you integrate by the total volume, then this is the total number of particles, and that dn by dt has to be 0. Okay, so now so that if we want the capital dn by dt to be 0, then sorry, we have dn by dt. So I'm now differentiating with respect to time, and that would be given by integral over volume. So I had a volume integration d cube r, but that volume element is not changing with time. So if I want to have this dn by dt, which I know is 0, because the number is neither created nor destroyed, then this is equal to what? This is equal to dn by dt. What is this equal to? It is telling you how at a particular location the density is changing, and that is changing because you are adding there is a flux inside that volume. Okay, Now, how is the flux calculated? So, the flux is basically, uh, what is the flux? Flux is you have number density into velocity. That is equal to the flux. You must have learnt it from, the flux of electric field line, etc., in that context. But in a fluid dynamics, the usage of this term flux is in a and somewhat more general, and it denotes that how much of if there is a particular field, then the rate at which it is it's passing through a particular region. So this becomes this is basically time derivative here, dq bar, and plus there will be a, this basically will be equal to the divergence of the flux that is coming. If there is no divergence, that would mean that whatever is coming inside is the same amount is leaving. But if divergence is finite, then you will have this should be equal to divergence of NV, and that is dq bar, and that has to be 0. So this tells you that what is here changing with time. The second term is that how much of flux is entering a particular volume and how much of it is leaving it. Okay, so if you recall, if I could have also done it a surface integral, something like a surface integral. That would be like if I integrate over the surface and then I calculate n u and then dot ds. What is the surface direction? Surface normal is outward. So if nu is coming inside, it will tell you, u dot ds will give you the flux which is entering inside. If it is positive, if it is negative, then it is the other way around. So if you are integrating over the entire surface over a closed volume, then this tells you that how much of the particle is coming inside. But this can also be written as a divergence of nu and integral over the volume. So that's what I have done here. But this total has to be 0. Now what does it mean? This means that I have a volume integral, and this is like dn by dt plus divergence of nv, and that integrated over a volume. Okay. Now this volume integral I could have taken any arbitrary, the system size could have any arbitrary value, right? So the integrand, if the total integral is 0 for any, the system volume is arbitrary, then it means that the integrand itself has to be 0. right? So this would imply that you would have dn by dt and plus divergence of n v is equal to 0. This equation is well known. I think most of you must be knowing it also. This is the known as the, what is it known as? Continuity.
Continue.
Yes. So this is generally a this equation tells you that this is a statement of the conservation of a number density or a mass density. So this is also a very important part of fluid dynamics. This equation, we have to couple it with the momentum equation. Okay, so this is one part. Now in momentum equation, where is n coming? It was coming here. P also, the pressure is dependent on n. So the equation of continuity and the momentum equation are coupled in some sense. You have velocity evolution, which depends on n, and the evolution of n, which depends on v. So there is a coupling. Now let's try to understand this appearance of this term in the fluid equation in somewhat deeper way. How do we figure that out? We had talked about it in the earlier lecture to some extent, but let me discuss it once more. And so let's insert a slide here. So how does the pressure term arise? Okay, how does the pressure term arise in the equation of momentum? See, in a particle picture, it was not there. How has it arisen now? Actually, we were forgetting something in a particle picture. If you have large number of particles, they would collide. And they would also collide with the walls of the material walls of the system volume, and they will also collide amongst themselves. Okay, and that was like a friction term or whatever term that you get in normal case. But when you have a large number of particles, this is a way, I mean, the collision is a way in which you are transferring momentum to other particles. From some particle, it is going to other particle. And so there is a force which gets imparted. And pressure is what? Pressure is force per unit area. Okay. And this is arising, I mean, like the units of pressure is force per unit area. But when we talk about pressure, we generally refer to the thermal pressure. So if you have lots of particles and you pack up, let's say in a balloon or something, then the thermal pressure of the particles basically inflates the balloon. So if you add more particles, the pressure increases more, and the balloon inflates more, and so on. So usually one uses the terminology of pressure for thermal pressure in this context. And let's now see how it arises. Okay, so we have, choose a geometry, and this is the geometry. You have x-axis, you have y-axis, and you have z-axis. And you have, I just construct a box just to show it's a, let's say, a virtual box. The particles are everywhere, but I consider a virtual box in this, and that virtual box, let me draw. So this is the virtual box here, and this is there. Okay, this is the box, and this is there. Okay, now we have two walls in this box, and that is this. Again, I selected just to show you. So I have this wall, and then I have this wall in the box. Okay, this is the walls. Okay, and where are they located? The center of this is x0. So it's at x0 minus delta x, this wall, and it is at x0 plus delta x. This width here is delta z. This width here is delta y. Okay, and I call this walls as A and B. Now, suppose you have, the particles in a thermal, if the particles have certain temperature, then they are all moving in the random directions. And if it's in a thermal equilibrium, you know that they follow the Maxwell's velocity distribution function. Okay, so the particles are entering this fluid element, they are leaving it, and so on and so forth, and they are all, this all is in because they are in thermal motion. Now we try to figure out that what is the number of particles which are coming and entering through the surface A. Okay, they are bombarding it like that, and they are entering it in the surface. What is that? So let's say per unit time. Per unit time, that means the velocity here, let's say, is Vx. And the number of particle with velocity Vx is, let's say, delta NV. And I have to multiply by area. Vx means what? Vx means distance travel along x in unit time. Okay, so the number of particles which are entering here is the number of particles having velocity Vx, which, let's say, because particles have different velocities, so I have not yet integrated over Vx. So delta NV, Vx, and that the area. Area is delta y and delta z. So basically, these many particles have a velocity Vx, x component of velocity is Vx, and they are crossing the surface A. Okay. And So what is delta NV? Delta NV is basically the number of particles having velocity Vx, right? So if you have a distribution function, then that is like integrating over all their y and z components. So you have a distribution function for the particles having velocity Vx. You must have done it in your statistical mechanics classes. Vy, Vz, and then you have integrated, let's say, over all dvy and dvz. But you have not integrated over Vx. And what is the number of particle which has velocity in some width around Vx? So we simply multiply here by some delta Vx. Okay. So that's delta NV. Now each particle carries a momentum. How much momentum does it carry? Each particle carries a momentum of mvx, right? Each particle. They carry a momentum of mvx. So the total momentum that is imparted on the surface, see, it's a virtual surface, but it tells you, I mean, like, what is force? I mean, change of momentum per unit time. So that, I mean, how much of particles are crossing? They are imparting some momentum in the surface. And so what is the total momentum imparted on the surface A is for those particles which are moving in the positive x direction is something like you will sum over I mean, it will be sum over delta NV, all the particles, and then there will be a mvx, which is the momenta, and then you will have this. So it will become Vx square, and then you will have delta y and delta z. So this many particles were crossing. Now you are evaluating what is the momenta that is arising from this side to this side. Then you have to multiply this by the mvx and then integrate or sum over all these particle species, right? So that gives you the total momenta which is along this direction. So that you can write as delta y, delta z, and it is like m vx square, right? And n, you average it over vx square, okay? And there's, because it's a random value, you will get a half n, let's say, and this is coming from x naught minus delta x. Here entering, okay? Why have I put a factor of half? The total density is n, but I've put a factor of half because I'm calculating Vx square. Half the particle would be coming this side and half on an average would be going this side. So it's only half n that would impart a momentum which is coming this side. If the velocity distribution is some isotropic, okay? Similarly, you will have the momenta carried in the positive direction. This bus means positive x direction. So momenta carried along the positive direction, PB plus, will be equal to, this will again be delta y and delta z, and then I will average again over m b x square and half n. But now this is calculated at x naught plus delta x, because it is this surface. Okay. So the momenta coming from this side to this side is PA plus, and at this surface it is going here, it is PB plus. So what is the net gain in momentum in this small piece of volume? That will be PA plus minus PB plus, right? That is the gain. So the net gain in momentum in this volume area is, you have to take P A plus minus P B plus. And what is that? That turns out to be delta y delta z and you have a factor which is n v x square at x naught minus delta x and minus there's a half m also, right? N is there, half m. So let me write that also, half. All right. Here, m minus n v x square at x naught plus delta x. So this is the net gain in momentum in this region of the volume. Now this again the other gain will be what? Other gain will be something is entering here. Right now we consider only the particles entering here and leaving here, right? Because Vx was all in the positive direction. There will be equal amount, if the system is isotropic, of particles coming from this side and leaving here, right? So they may also lead to some net momenta gain here. So the net momenta gain will be twice this. Okay. So that takes gets rid of this factor of half here, and so the total change of the momenta of the fluid element which is here located at x naught, will observe a total change in the momenta, which is, what is the total momenta? That is density times, and this is all x momenta that I'm talking about. So density times mass times Vx, and that integrated over delta x, delta y, and delta z. Why? See, this is the volume. This is the volume here. Okay. And so it is delta x, delta y, delta z. And then you have n number of particles with mass m moving with velocity vx. That is the momenta. And how does it change in time? That is given by this expression. So this bolo.
Ma'am, you have written here net gain in momenta. Yeah, I mean it should be, I think, net change in momenta.
Net change. Gain in momenta or like net. Because if I'm talking about whatever is how much of momenta along Vx that you gained. If Vx positive, I'm looking at, okay? So the rate of change of momenta in this fluid element would be given by, you will have this term because this is minus m, and there will be a, what is this? I'm evaluating n Vx square at x naught minus delta x, and then I'm evaluating at x naught plus delta x. If you recall the definition of derivatives, then in the limit delta x is tending to 0, this is some sort of a derivative, but with a negative sign, because if you write something like d psi by dx, then you will write psi at x naught plus delta x, and then minus psi naught at minus delta x, and then that will be 2 delta x. But here the minus 1 is coming ahead, so you will have a derivative with a negative sign. Okay, so you will have delta y, and I have to divide by delta x also, delta z, so I'm multiplying by delta x, so that becomes a volume, and then d by dx of this will be n Vx square average. What have I averaged over? I have averaged over the distribution function, right? So I have averaged it over the distribution function. Now, what is Vx? In a fluid element, if you are treating this as a fluid, then in a fluid element, Vx is the velocity of particles as we had discussed it here. And that velocity will comprise of the thermal motion of the particle as well as the fluid motion of the particle. The fluid itself may be transported. That velocity doesn't get defined in the thermal velocity of the particle. So we have to be very careful. So your When you write a particle velocity Vx, we had written this was a particle velocity Vx. Okay, that will correspond to, so it's the x component of the particle velocity. This will have a fluid velocity Ux and plus the random thermal velocity, which will be Vx, something like a thermal velocity. If I average over Vx, then it will be simply Ux, which is the fluid velocity. But if I'm averaging the square, okay, I'm averaging the square of Vx, right? And if you remember, how is temperature defined? Temperature is defined in terms of the thermal velocity as half m V thermal square average is equal to something like half Boltzmann constant K B T, right? So if you look at this equation, this and this and this cancels out. M is also constant, so it cancels out. Okay, and what are you left with? You are left with d by dt of n Vx, right? And I have to average over this. So my equation becomes something like, if you average over Vx here and use this equation, so this becomes d by dt and n, which is a fluid thing, and the average of velocity over the distribution function. This average is over the velocity distribution function. This simply becomes Ux. This, and the right hand side becomes minus d by dx, and we had average over n and Vx square average over the distribution function. What would be Vx square average? From here, you see, if you take Vx square and then average, then basically you are averaging Ux square, which is a fluid value that is there. Then you are having 2Ux and then Vx thermal, and then average over this. This is 0 because this is average over a velocity. And then you have Vx thermal square average. So this is directly related to temperature. So when you do this, here I can then write this as ux square plus, what is Vx thermal square? It is simply kBT by N. So this becomes kBT by N. Right? Now if you expand this, this has two components, dN by dt ux plus n dux by dt, which is equal to minus d by dx of n ux square minus d by dx of k b t by n. Okay.
Ma'am, there should be a N there last time.
Oh, sorry. Yes. N. True. Now, what is dN by dt? Let's say we have averaged over all the velocity components, right? Vy, vz. So dN by dt will be simply d by dx of nux, right? You know it from the continuity equation that dN by dt is plus d by dx of n sorry, I had to open again. I will not write anything. Yes. It won't save also, is it? I don't know.
Ma'am, I think you should install the Office software. I think it's free for IT Delhi
It's
student.
not free. In Mac doesn't come free. In Mac you have to use only Office 365. It is not available for Mac system. I'm using Mac system. So they have asked me only to use the Office 365. And
Ma'am, Office 365 is available offline also, na?
huh?
Office 365 is available on the CSC website.
It may be available offline, but the point is that I have to use Office 365, which has certain constraints. Like it is PPT. I mean, like I always get stuck like this. So if in Mac system, if the professional version of PPT or doc or something, I cannot install, and that would not have these problems. Like now I'm stuck. Now even the file is not coming. I don't know. Let me
Okay,
open another window. Presentation 8. So I can kill it. So if you expand these terms, okay, so dn by dt would be minus d by dx of nux, right? So I have the left hand side is something like, okay, left hand side is, I have to replace this, right? So I should write dn by dt as minus d by dx of nux. So it should be ui. हाँ राजेंद्र बोलो।
हेलो मैडम प्लीज आप ज्वाइन कीजिए।
मैं बोला ना मेरी क्लास चल रही है, 3:30 के बाद आऊंगी।
ओह सॉरी सॉरी सॉरी, ओके ठीक है सॉरी।
हाँ ठीक है, ओके। So where were we? So I have to replace this by, so you can do the algebra, I think, and cancel out certain terms, and
Yes,
you
ma'am.
will get, I think, that simple algebra. So you will use the continuity equation, etc., and you cancel out certain terms, and what you will be left with finally is m n, or m I had already cancelled, but if I keep m n, then, and pressure is, let's say, n kb t. So I'll get an equation of this form, that it is du x by dt plus u x d u x by dt dx, and that is equal to minus dp by dx. So the x component of momenta will have an additional term which is minus dp by dx. Similarly, the y component of equation, I mean, like Maxwell's forces are already there. We were here just evaluating the rate of change of momenta, because there's some number of particles which are coming here, hitting this wall with a certain momenta, and a different number which is crossing the other side, and as you make the wall thickness go to 0, there is a net gain or net loss of momenta, and that is this gain momenta. From that we define, and we got an expression that this is equal to minus dp by dx. If you do it along y, then similarly, basically on all the three directions, you will get mn del uy by dt plus uy duy by dy, and that will be equal to here as minus dp by dy. And similarly for z. So if you add the equation as a vector, then you will get the equation which is m, and it is d. So you're multiplying this by I cap, this by j cap, and z component by k cap, and adding them together. Okay, then this becomes dv by dt plus v dot del v, and that is equal to minus grad p term. Okay, it has arisen because of the statistical nature of the particle, and so the complete equation has an additional term, this, and plus the conventional forces which are already acting on the particle. Okay? Conventional forces. What are the conventional forces for the charged particle? Usually, they are the Lorentz force. If it would have been heavier than mass and there is a gravity, then you will have mg also. Otherwise, this is it. And you have the continuity equation. Now, basically, when you are trying to solve a fluid, so this continuity equation in a vector thing will become NV. This is divergence is equal to 0. So sorry, here there is a mn. So if you divide by n, this is n. Okay. So here, as I said, there's a coupling. There's an n here, which is a function of time. M is not a function of time. N can be a function of space and time. And velocity, which is a function of space and time. In the n evolution, velocity is present. In the v evolution, density is present. And P is also given by n kbt. Often, this set will be closed when n is coupled to v is coupled to n. This set will appear close to you only when t is a constant or t is given to you. Okay, because then it is dependent on n here and this is dependent on v here. So this is okay, but often it may happen that your temperature is also a function of space and time, because you always see in a fluid, supposing you are heating a fluid, then at the bottom of the vessel the temperature is higher, at the top the temperature is different. So then temperature also becomes another field, and this field is dependent. Okay, so pressure is dependent on temperature and temperature is a dependent variable. But here in these two equations, I do not have any means to evaluate the evolution of temperature, right? So these two equations then are not closed. And so either you provide another set of equation which tells you the evolution of temperature. So that is also sometimes done, where you will see d capital T by dt and so on. And here you will be having terms which define what is the incoming heat and what is the cooling rate and so on, which tells you the evolution of temperature. So either you will have another evolution equation to define the how temperature evolves, or sometimes temperature is given by an equation of state. Okay, what are the famous some of the equation of states that you know? There could be a case where things are isothermal. That means temperature is constant. If T is constant, the value has been provided to you, so don't have to worry. T you get out and do it. Then there are phenomena where perhaps your process is adiabatic. Okay, so temperature is changing, but things are evolving according to the adiabatic equation of state. And you know the adiabatic equation of state, what is that? That again is what? There is a, what was that?
P to the power gamma equal to constant.
V to the power gamma was constant. Now you will say, what is V here? Right? V was a volume. Right? V was the volume for a given number of particles. So this becomes inverse of number density. So here it will translate to P by N to the power gamma. is a constant. So that's the adiabatic equation of state. And then again, so basically by using this, you will be substituting P in terms of N. So again, this set is closed. So this is how you do, and we will learn about it more in the next class. If you have any questions, you can ask that now. Bolo. Any questions on whatever I have taught till now?
No, ma'am.
So I repeat once again, what did we do? We are basically trying to obtain the fluid equations of motions as a big simplification for a large number of charged particles. It simplifies the system a lot because now you don't have to follow the entire number of particles, each and every particle, the evolution of each and every particle, which can have a very large number. But the fluid basically makes it more coarse. A fluid description makes the medium a little coarser. Like you're not seeing the individual molecules or atoms or particles. You are seeing as you see water. So you have small fluid elements and you are concentrating on only that. You are not looking at the kinetic picture. And this is we obtain the pressure term which comes in the fluid equation. So over and above the conventional forces, you will have to add a pressure term which is effective when you're going from a fluid description, from a particle description to a fluid description. The total derivative changes to partial and convective derivative form, so that you have to treat space also as an independent variable. So these are the things that you have to keep in mind, some of the preliminary things that you have to keep in mind. So you will see it's very interesting. We will use the fluid set of equations now to describe the electrons and ions, and you will see that we will be able to show that a variety of waves that can get excited in the plasma, and we will understand their characteristics and so on. Okay, so thank you.
Thank you, ma'am.
Okay,
Thank you, ma'am.
bye.
Bye.